Okay, so electronic design automation, this is the subject we will be talking about in the course of the next series of lectures. Before I go into the actual series of lectures, let me first tell you what exactly we intend to cover in this series of lectures. Well, electronic design automation, as the name implies, what it really means is that we have some kind of a design which we want to carry out. Starting from the specification, we want to arrive at the final design implementation. It can be an FPGA, it can be an ASIC, it can be anything. So, let us first try to have a quick look at what are the topics that we intend to cover in this course. First, of course, we would be looking at the digital circuit design flow, which means that if we have a digital design, digital circuit specification, what are the different steps that you need to follow in order to arrive at the implementation. Well, out here we will be considering only digital circuits, we would not be considering analog designs. Next, we would be looking at one popular hardware description language, namely Verilog. This description language we will be using as our vehicle in some of the future lectures. All examples we will be giving in Verilog. Next, we will be talking about some topics on logic synthesis. Now, assuming that you are already familiar with two-level logic minimization, we will be starting from that point onwards. We will be talking about multi-level optimization, a process called technology mapping, and of course, something called high-level synthesis. Well, in high-level synthesis, we are trying to arrive at a design, a register transfer level design starting from a behavioral specification. Then of course, we would be considering or talking about a very important issue, that once we have designed the circuit up to a particular level, how do we test it? So, some issues related to testability. And at the very end, we will be talking about physical design automation, which concerns the issues that comes in at the last phase of the implementation, namely here we talk about the floor planning, placement, routing. These issues are arising when we consider the silicon floor, how do you place the different components on the floor of the silicon, how do you interconnect them, these issues would come in here. Okay. So, let me give you a list of some references. Of course, this course is so diverse, it is not possible to specify one or a very few books to cover all of them. So, I have got a comprehensive list of references, you can have a look at these. So, the first three references would be concentrating on the design and synthesis aspects. The fourth one would talk about the Verilog description language. The fifth one is again synthesis, this concerns high level synthesis. Then we have some more references. There are two books which I have referred here for testability analysis, testable design, and the last three books are concerning physical design automation, placement, layout, routing, etc. Okay. So, during the course of this course we would be referring to these books as and when required. Okay. So, to start with, we begin by talking something about digital circuit design flow. Okay. So, we look at the digital design process from the perspective of a designer. Now, as you know that with the advent of the VLSI technology, nowadays the complexity of design is being increasing very rapidly over the years. Now, today it is possible to have chips which can house more than a million transistors, multi-million transistor systems are possible on a chip. So, design complexity is growing. Design complexity has two you can say two dimensions. One is of course the increased size and the increasing complexity to handle a design of that size. Okay. Now in earlier days when the designs were small, many of the designs could have been done using some kind of manual technique or semi automated technique with frequent manual intervention. But what has happened today with the increasing size of the designs is that nowadays it is absolutely essential to have computer aided design tools to assist the design process. So, without the computer aided design tools you really cannot handle a design of that complexity. So, if you look at the way a designer proceeds with designing a typical chip or a circuit nowadays, there is a conscious effort to standardize the design flow. Design flow, as I mentioned just previously, it is basically the process which you follow starting from the specification down to the implementation. What are the different intermediate steps? Now, depending on the kinds of CAD tools you have, depending on the kind of chip you are trying to design, the design flow can vary quite widely. So, it is essential or necessary to standardize the design flow before you are actually trying to design the chips. So, just as I mentioned, design flow is essentially the design procedure, stepwise procedure which you follow starting from the design idea or specification, whatever you call, down to the actual implementation. Now, actual implementation when we are talking about, well, again I have told you this can be an application specific integrated circuit, it can be a field programmable gate array, or it can be any other kinds of programmable logic like PLDs or any other thing. But the idea is this: you have a design idea which you specify in some form, and using a sequence of steps using the CAD tools you finally arrive at the actual implementation at the very end. Now, out here I show a few of the steps which are followed. There are a few more steps also. Of course, the first step is the design specification. Then you carry out synthesis, which is essentially a design translation from the specification to some kind of a netlist, some kind of a register transfer level or a gate level design. Then you typically carry out simulation to check whether the synthesized design is correct or not. There can be some problem with the CAD tool also. You must be 100% sure before you actually go for the implementation or the manufacturing of the chips. Okay. Now, the simulation can be done at a number of different levels. This we will be looking at in some more detail later, because you can also decide to do the simulation after specification itself in order to check whether the specification is correct. You can do the simulation after synthesis. Well, after the synthesis, the step after that is typically layout, where you are thinking about how to place the blocks you have synthesized onto the floor of the silicon, or in case of FPGA, well, how to place or map the sub circuits into the basic cells of the FPGA. Okay. So, these are the layout concerns. Now, during synthesis and layout itself, you often also consider some issues related to testability. This means when you are designing the circuit, well, the circuit is functionally working correctly or not, that is one issue. The design is correct or not, that of course is a very big issue. But after manufacturing there can be a number of defects. There can be some short circuit in the wires, there can be open circuit, there can be a lot of other problems in the transistors. So, after manufacturing you have to test the chips. Now, here I have just told you that you today have chips which can house millions of transistors, but externally you can have only a few hundred pins available to you. So, just using those few hundred pins, how do you test those million components inside? there has to be some special design effort that has to go in during the synthesis process itself, so that during testing it becomes easier for the test engineer to test the chip. There are a number of techniques called design for testability, built-in self-test. These are the things we will be discussing. And there are.
What did you say, that the design process are such that the testability can be made easier?
Okay, that exactly what I have said is that designs are big nowadays. So unless the designer puts in some special module, some special design, you can say design procedures or design rules in the process of synthesis, it may become impossible for the test engineer to test the chip. Just if I give you any arbitrary chip and ask you to test it, it can become a very big problem for you. But if during the design process itself I have incorporated some feature in the chip, just using which you can test it easily, it can become very easy for you for testing. Okay, fine. Now, as I had mentioned that with the increased size of the chips and the increasing complexity, the CAD tools are essential. There is a new generation or a new series of CAD tools which is now available in the market, which are used by the designers to go through the digital design flow process. Now, all these tools are based on some so called hardware description languages. Well, hardware description language means you have a standard way of specifying things. That thing may be your design specification, that may be your synthesized netlist, that may be the layout, it can be anything, but you have some standardized formats in the form of some language. Well, basically this hardware description language, they provide ways of representing the design at several different levels. Okay, this we will see later that how. So, I have mentioned as we go through the different design steps, your design goes on refining from the behavior to register transfer level to gate level to layout. Now, if at each level you can represent the design properly using a description language, it becomes a consistent format. Well, here one advantage you gain additional is that if you follow some standard, your internal representation may be portable across different CAD tools from different vendors. Say that one part of a design flow you can do using the CAD tool supplied by vendor A, the other part you can do using a CAD tool supplied by vendor B. So, if you are following some standard, then you have complete portability and interoperability. Okay. And typically, as I mentioned, as you go from top to down, from the behavior down to the layout, you typically go through a series of transformational steps where each succeeding step will contain more detailed hardware implementation, or means hardware information as compared to the previous level, from behavior to register transfer level to gate level to transistor level, and so on. So, these are some of the typical steps of transformation: behavioral to RTL, RTL to gate level to transistor level, then finally you can have another level, transistor level to the final layout, geometries of those layout, the layers. Okay, fine. So, let us first talk about the hardware description languages. Now, you may be knowing that today in the market there are two competing HDLs which have become very popular. One is called Verilog, other is VHDL. Now, in this course, well here we may choose to use any one of them, but in this course we will be using the language Verilog for illustrations. Well, you can do the same using VHDL also, there is no problem. Verilog and VHDL are two different languages with slightly different features. I would be talking about some of the differences, that what are the basic difference between these languages, but this will come a little later. Okay. So, let me now show diagrammatically a simplistic view of the design flow. Well, I am calling it simplistic view because this design flow looks like a unidirectional process starting from top to bottom. This is the direction of the flow. But in a typical design process, there can be a few other steps in between, and also there can be feedback. But in the simplistic flow, I have not shown the feedback path. Well, here my idea is to emphasize what are the different steps of the process you need to go from a design idea into the final implementation. Okay. So, here as you can see that from the design idea, the first thing you try to do is to translate it into a behavioral specification. This behavioral specification is typically in the form of hardware description language, as I told you, either in VHDL or Verilog. Then you go through a step of synthesis. This is one step of synthesis where from the behavior you arrive at a so called data path design or a register transfer level design, where your basic building blocks are registers, arithmetic logic units, multiplexers, flip flops and so on. So, this is a slightly higher level design. Okay. And from the register transfer level design, data path design, you typically translate it into logic design, where you get a netlist of gates and flip flops. Later on, from logic design, you will have to finally translate it into physical design, where you talk about the transistor, their layout, etc. And after you have the final transistor layout, you will have to submit the final design specification to the fabrication facility, where the chip will get fabricated. This is the process of manufacturing. So, finally, after the process of manufacturing, you will get either the chip or a collection of chips in the form of a printed circuit board. And these are the intermediate forms you can see. After the behavioral design, you can get during synthesis something called a flow graph or a pseudo code representing the netlist. So, after RTL design, you get a structure, register structure, which consists of registers, ALUs, arithmetic units, multiplexers. They may be interconnected by buses. Logic design will generate a netlist with gates and flip flops. Physical design will talk about transistors and their layouts and so on. So, this is a simplistic view of design flow.
So, data path design is the RT level?
Data path design is the same as the RTL level design, register transfer level design. Yes. Okay. Now, before actually going through the steps, let us look at the design process from a slightly different perspective. See, a design, this design may be in the behavioral level, it can be in the structural level, it can be in the logic level, it can be even in the layout level. But in whatever level you are, now a design can be represented at 3 different levels of abstraction. Well, you can view a design from the point of view of its behavior, from the point of view of its structure, and from the point of view of its physical implementation. There are 3 different views you have in order to look at a design. Now, there is a standard way of looking at these 3 different angles of a particular design. This is represented by something called a Y diagram. I am showing the structure of a Y diagram. I will be coming this into detail later when we talk about synthesis. So, a Y diagram looks something like this. As you can see, it looks like a Y with the 3 directions representing behavior, structural and the physical domains. Now, the idea is that when you are talking about the behavioral domain, there we are talking about the behavioral specification of the design. Now, here I am not talking about the details later. Well, here we typically specify the behavior in the form of a description language like Verilog, VHDL. Well, if you are talking about logic, gate level design, There also we can specify behavior that can be in the form of a truth table, that can be in the form of a Boolean expression, that does not talk about the actual implementation, just the behavior. So, in the behavioral domain, we talk about how the circuit should function, its input output behavior in some way. Now, when we talk about the structural domain, this means we have already undergone a step of synthesis. Now, we have some kind of a netlist with us. Well, if it is a behavioral level, then we talk about interconnection of big subsystems, big blocks and how they are interconnected. Now, if we are at the register transfer level, then we talk about ALUs, registers, adders, their interconnection. Now, if you are at the logic level, we talk about gates, flip flops and their interconnection, and if you are at the physical level, we talk about transistors and their interconnection. Okay. Now,
Can you please repeat this?
yes, sure. See, behavioral level means I am trying to specify the behavior of the design. Now, this behavior can be specified in a number of different levels. Well, in a high level I can talk about the system. Well, I can express my behavior in an algorithmic fashion, something like you are writing a program in a high level language similar to that. Well, the one step down I can specify the behavior in the form of, say, some basic building blocks. There each of the basic building blocks I am specifying in terms of its behavior. Like a ALU I am specifying in terms of the behavior, a register I am representing in terms of behavior. I am not going into the detail of it, okay, and their interconnection. Now, at the next lower level I can think of the behavior of a logic level implementation. There I can represent the design in the form of a truth table or in the form of, say, an Boolean expression. Okay. Now, this is behavior. Now, when we are into the structural domain, so at least we have a part of the synthesis which is done. Now, we can look at a netlist. Well, at the logic level we can see some gates and their interconnections. Well, at the RTL level we can see the blocks and their interconnections. Well, at the transistor level we can see transistors and their interconnections. That is the structural domain. Now, at the physical domain, this is the angle which you look from the point of view of the physical implementation. Like, if you consider that this is my silicon floor, this is the floor of the silicon where I want to finally map my design into. So, when I am into the high level design step, behavior, system, subsystems, there what you can do at the level of the chip, we can do some floor planning, that one subsystem I will be placing here, one subsystem I will be placing here, one subsystem I will be placing here. But these subsystems are still black boxes to me. Now, once we are into one level down the specification, then each of these subsystems can be broken up into smaller subsystems. Okay. Now, this process will continue till we go down to the level of the transistors and the layouts. So, we will get the final layout at that level. So, at the physical domain, we are looking at the actual floor of the silicon and how we are placing the blocks which are at the level of abstraction we are looking at onto the floor of the silicon. That can be at a high level, that can be at a very low level, right. So, this Y diagram is just a way of looking at it. It's nothing special in that. Okay, so now let us look at some explanation regarding these three domains with some examples. Well, I have illustrated the differences. Let us now take some examples. Well, let us start with the behavior. Now, as I said that in the behavioral representation, we are not specifying any details of the implementation. We are just specifying the input output behavior of the system. That may be in the form of an algorithm, that may be in the form of a truth table, in the form of some Boolean expression. So, it specifies how the design should respond to a given sets of inputs. If I give some input, what is the expected output? That is the behavior, right. Now, as I mentioned, Behavior can be specified in a number of different levels by means of Boolean expressions, by means of some kind of truth tables. It can be specified algorithmically in some high level language or in some hardware description language. Well, you can specify behavior in a number of different ways. Now, let us take some concrete examples of representing this behavior. Well, here we take a simple example just to illustrate. Here we want to construct an n bit adder by cascading n number of full adders. 1 bit adder means full adder. Now, as you know that a full adder will be having 3 inputs and 2 outputs. The 3 inputs are the 2 numbers a and b, 2 bits you want to add, and a carry input, and the outputs will be sum and a carry out. So, as you know that the logic expressions for the sum and carry are these, right. Well, I am illustrating the generation of the carry logic only. You can also do the same for the sum logic. Well, the example that I am giving, there I am specifying how I can generate the carry logic for a 1 bit adder, single 1 bit adder. This can be extended by using a number of such instantiations to create an n bit adder also, but just for illustrating I am showing you for the time being that how to generate this carry out for a 1 bit adder, for a full adder, and I am using the language Verilog for illustration. I will be talking about the syntax of Verilog later, but for the time being I am showing you how to specify. This is an algorithmic level description of carry, where as you can see here I have specified the Boolean expression. This ampersand means AND, this bar means OR. So, AB or BC or CA. This is how we specify this in Verilog. This is a module. In Verilog everything is in terms of a module. This is the name of the module. These are the parameters, just like you specify a function. These are the input parameters, these are the inputs to the block, this is the output. This is a keyword assign, this you assign to CY. Right? So, this is one way of specifying the carry in terms of its behavior. Okay? There is an alternative way of specifying it also in the form of behavior, namely in the form of a truth table. That you can do like this. So, here well, like when we specify it in the form of truth table, instead of a module we declare it as a primitive, right, begin primitive, end primitive, some kind of. The rest is similar here. These are the parameters, these are the inputs, these are the outputs, and the input output behavior we specify by using a keyword table and end table. Now, this table will remember that how many inputs I had and how many outputs I had. There were 4. Double slash means comment. This is a comment line. This line is nothing but a comment. Just look at the other lines. First you specify the inputs, then a colon, then the output, followed by a semicolon. So, this can be an incompletely specified truth table. With you can see somehow there is a question mark, which means do not care. This says if A and B are 1, C is a do not care, then the carry out will be, sorry, this should be CY. Carry out will be 1. Similarly, if A and C are 1, B do not care, then it will be 1. If 2 of them are 0, then the output will be 0. So, as you can see, you have specified all possibilities, but we did not specify all 8 columns or all 8 rows of the table. Okay? Because the all 0 case will get covered by these, the all 1 case will get covered by the first 3, right? Fine.
Sir,
yes.
primitive is used for Boolean behavior and module is used for algorithm.
Primitive is used for something which is like a constant, where you specify exactly the input output behavior in terms of the numbers or the values. Now, in the earlier example you had specified in the form of a Boolean expression, where you need to evaluate the expression in order to find out the value. But in case of primitive, it is something like constant values you specify. that if this is the input, this is the output. Okay. Fine. So, these are some examples of representing a design by its behavior. Now, let us talk about structure. Now, in this structural representation, here we have some components. Now, the kind of the components we have, that depends at which level of design we are in. Now, if we are at the logic level, our components are gates and flip-flops. If you are at the register transfer level, our components are ALUs, adders, multiplexers, etc. So, here you specify components and how they are interconnected. This interconnection is sometimes called a netlist. Netlist is nothing but a graph. You specify some nodes and their interconnection. Now, these nodes will be the components, this will be gates. Okay. So, now as I mentioned, the netlist can be specified at various levels depending on at which level you are considering the components. Components can be as low as the transistors or the gates, or it can be as high as say an ALU or even a subsystem. Okay. So, just as I mentioned, this structural representation you can represent it at the level of modules at a very high level. Modules can be very high level, it can be the RTL level modules also. You can represent it at the gate level. Switch level means the transistor level. This switch and transistors are used synonymously. So, when we are talking about switch level design, we are actually talking about a netlist of transistors. But when you have translated this transistor level design into actual physical layout, then we are at the circuit level. So, it is very clear, as you go from the module level down to the circuit level, more and more design details are getting revealed, right. Okay. Now, here let us take a very simple example. Say we want to design a 4-bit adder. The root of this tree represents that specification. Add 4 represents a 4-bit adder. Now, to keep things simple, we are designing it as a ripple carry adder. We are using 4 such, we will be using 4 full adders and interconnect them, okay, by rippling the carry. So, the 4-bit adder can be broken down into 4 full adders and their interconnection. So, here we are talking about structure level. So, at the first level of abstraction, you can break it down into 4 full adders and their interconnection. Well, if we want to go down further, then each of these full adders can be broken down further into a carry subcircuit and a sum subcircuit. Now, each of this carry and sum subcircuit can be further broken down into its equivalent logic level. Just as for example, the carry subcircuit looks like this, AB or BC or CA, right. Similarly, you can design a subcircuit for sum. So, this is your structure level design. So, as you go down, the size of the building blocks, at this level it were full adders, at this level it were the carry and sum blocks, at the lower level it was the gates. So, you have smaller and smaller building blocks and the netlist is becoming bigger and bigger in terms of the number of components, right. Okay. So, this kind of a design specification you can represent very easily in a hardware description language. I am giving an example with Verilog. Okay. This is a design description using Verilog. If you look at it, you will understand what we mean. This is a module which is a 4-bit adder. We are giving it a name add4. These are the parameters. This is the carry in. These are the 2 inputs we want to add. Now, since this is a 4-bit adder, the inputs will have to be 4-bit vectors. So, as you can see, this x and y are defined as input within bracket 3:0. It means it is a 4-bit vector with the indices starting from 0 going up to 3, x0, x1, x2, x3 and y0, y1, y2, y3. Similarly, carry in is a single bit. The sum will again be a 4-bit quantity, and cy4 is the carry out. Okay. This wire, these are some say this is a black box we are considering. We have a vector y, we have x and a vector y, we have carry in, and then the output we have a vector s and we have a carry out cy4. Now, inside, well, see, just look at these 4 lines. Here what we are doing, we are creating 4 instantiations of this low level add module. Add is a full adder. So, what we are saying that in this block we are instantiating this add 4 times, right. These are the names we are giving, B0, B1, B2, B3. And just before coming back to this, let me show you another slide first. This adder must be predefined as a module, as another module. This is a full adder module which I have already defined, where the first parameter represents the carry out, then sum, then the 2 inputs and the carry in, right. And similarly, the carry, see here this adder, if you just look into the detail, here I have not specified the Boolean expression. I could have, but I have decided to use a separate module for carry and a separate module for sum and use it here. These are examples of instantiations. Instantiate. Just like we are calling a function from another function, we are just including a module inside this module. So, we are including the sum, we are including the carry, and we are using the parameters in a proper way, so that these parameters and these can get proper correspondence. Well, here I am showing the code for carry. For sum I am not showing, sum will be very similar. Carry here at the lowest level, you have a choice of specifying the circuit in terms of gates, or you have a choice of specifying in terms of behavior in terms of Boolean expression. Well, here this AND and OR are primitive gates which are already available in the library. These you need not explain any further, these are already there. So, if you look at this AND T1 AB, this means G1 is an AND gate with inputs A and B and output is T1. Similarly, G2 is another AND gate, inputs are A and C, output is T2. G3 is another, B and C are the inputs, output is T3. And G4 is an OR gate, it is a 3 input OR gate, it takes T1, T2, T3 as the inputs, and as output it generates carry out. Now, as you can see, this T1, T2, T3 were not any input or output parameters, they are intermediate lines. These are defined as wires, right. So, wires are essentially the signal lines which are used for interconnecting one module with another internally. So, this is how you can define a carry, a full adder, and using this and the interconnections you can, at a higher level, you can define 4 full adder modules and their interconnections. See, interconnections are defined in the way you specify these parameters. Just to see, B0 has this CY out 0 as the carry out, B1 has this CY out 0 as its carry in, so the carry is getting changed. Similarly, this CY out 1 is getting as the carry in here, the carry out of this is getting as carry in here. So, these 4 full adder modules we are doing a ripple carry chain by specifying the parameters in a proper way, right.
So, this is at the RTL level. first level of the structure.
This is at the RTL level, yes. So maybe at the top level of the design you do this, but as you go down the design you will be breaking up these adds into this. At the next level you will be splitting the sum and carry into this. So this step goes on. But the beauty of this language Verilog is that you can capture the information in the same language. So in the same language you can specify things at a number of different levels. There is a version of Verilog using which you can also specify the physical layout. I will just show an example shortly. Fine. So the third step that I was talking about was the physical representation in the Y diagram. So we talked about behavior, we talked about structure, we talked about physical. Well, here just before I proceed further, let me tell you one thing, that if your objective is to design a chip, then it is always instructive and it is always better to design or to specify in the structure level as far as possible, because you may be tempted to specify in the form of the behavior, because all of you are so very familiar with writing a program in a high level language. So if I give you a complex design to implement, then you may be tempted to write it like you write a program in C. But the problem is that the synthesizer, while synthesizing, can face a lot of problems. But if you have some kind of a block diagram, hardware block diagram in the back of your mind, you can specify it at the structure level to the extent possible, then you can get an implementation which will be efficient. Well, if you specify the behavior level, most likely you will be getting a very inefficient implementation, right? Fine. So in the physical domain we talk about physical representation, and there I had mentioned with the help of an example earlier that when you are at the module level, when you are at the RTL level, then at the level of the silicon floor we can represent each of the 4 full adders as rectangular regions or polygons. These are the 4 full adders. As you go down, as you go to the carry and sum, then each full adder will be divided up into a carry and sum, carry and sum, carry and sum, carry and sum. Then at the logic level each of these will be divided into gates. Okay. So these steps are going on, and in the physical representation at all levels you are thinking that exactly where on the floor of the silicon I am going to map them. And finally when you are at the layout level, at the lowest level, then you have the actual layers, metal, polysilicon, diffusion, etc. Now the ways in which the lowest level layout is represented is also not very difficult. They are represented as some geometrical shapes. They are all rectangles, a collection of rectangles. A line can be defined as a rectangle whose width is less but length is long. You specify the exact coordinates, just like you specify a drawing. So I am giving you an example. This is of course a hypothetical example, this is not the exact one. I am only showing you a small part of it, that how a physical representation can be modeled in Verilog. Like here also you have the module. Well, here I just forgot to add the input and output parameters. They will be as usual. Okay, input and output is not mentioned here. Boundary specifies the coordinates of the bounding box inside which you want to place the layout, 0 0 to 135. These are the xy coordinates, and these are the ports. That means exactly where on this bounding box are the input output points located. These are called the input and output ports. So you specify the exact coordinate of those, and you also specify on which layer the ports are available. For example, this one is available on metal, aluminum, width of 1. This one is available on polysilicon, width of 2. And there can be some other submodules you may be adding, A0, A1 for example. A01 can be anything. Oh, sorry, not A01, add. These adds are full adders. you can add one full adder at an origin 0 0. Say you add one here. If this represents 0 0, then you can add one full adder here, and another full adder you can add at a coordinate 0 120. It can be somewhere here. This can be 0 120. So at this level you specify the exact coordinates, and you specify at exactly at which coordinate you have the blocks. Now these blocks can be high level blocks, it can be in the form of rectangles of aluminum polysilicon diffusion also, right. So here we will not be going into detail at this level, but just for your information I mentioned this. Just to summarize, digital IC design flow, these were the steps, some of the steps I had mentioned. This is a slightly refined diagram. Just I finished this lecture with this slide. See, to begin with, you do design entry where you specify your design in terms of its behavior. Then you go through a process of synthesis. This is sometimes called logic synthesis because the RTL level synthesis and logic synthesis are they typically combined together. So there what you get as the net output is a net list of gates. Fine. So after you get it, you typically do some kind of a circuit partitioning because your overall netlist may be too big. Well, out here you do some kind of a graph partitioning to identify the tightly coupled modules, and the number of interconnection between two modules are less, so that it will be easier for you to place these modules on the floor of the chip. Typically either after partitioning or before partitioning, you do something called pre-layout simulation to verify whether your behavior or the process of synthesis was correct or is there anything wrong. Now you will see that if you specify a design in Verilog, there are some features which are perfectly okay when you specify it, but during synthesis it will give error, it cannot be synthesized. These are the things we will be discussing later. So you carry out a pre-layout simulation, and if you get any errors or inconsistency, you can modify either your original design specification or you can make some changes at the logic synthesis level also in order to rectify that defect. And after you are done with this, you are now going to the actual layout implementation on the floor of the silicon. There you actually go through processes like floor planning, placement and routing. So at the end of which you get the actual layout in terms of the rectangles as I have just mentioned, silicon, polysilicon, diffusion, metal, etc. But as you know, the process of fabrication is expensive. Well, if you give a chip for fabrication, it will cost you, it may cost you several lakhs of rupees. So before going there, you must be sure that your layout is also correct. So normally you go through a process called circuit extraction. Circuit extraction means from the layout, from those geometries, you try to re-extract the transistor level circuit. Like for example, if a polysilicon and a diffusion rectangle intersect, it means there is a transistor at the junction. That way it is very easy to extract the transistor level layout from there. And it means you can also estimate a very accurate figures of the interconnect resistances and capacitances because you know the exact geometries now. Say that for a polysilicon line you know the resistance per unit length, you know that exactly for how long the line is running, you can estimate the total resistance. So after circuit extraction you can do a post layout simulation. But the problem here is that here you have a circuit which consists of transistors, resistances and capacitances. So here you will have to do something called a circuit simulation using a software like SPICE or something. This is time consuming, this can only handle small circuits. So you will have to use this very judiciously.
So,
yes.
What is the difference between floor planning and placement?
Floor planning means floor planning is a tentative plan that exactly where you want to place the blocks. Placement means as you go through this step of synthesis, the say what I exactly mean to say is something like this. Suppose this was the floor of the chip. So, at the level of floor planning, you have defined that this is a place where you will be placing a module M1. This is a place where you will be placing module M2. This is just a plan, just like a building plan you have done. But as you go through the process of synthesis further, you will be going down to gates, to transistors, to layout. There you will be getting the exact shape of the module. So that after the placement is over, possibly your modules will look like this. This will be now your M1, this will be your M2, and these will be the interconnecting ports. So, you will be now interconnecting them like this, like this. So, floor planning is a tentative relative relative ordering or positioning, and placement, well you can do placement once you know the exact geometries and the exact points which need to be interconnected. Okay.
So the routing information will be in the placement, or the
routing will be done after placement.
So this interconnects will be done after the placement.
After the placement is done.
So this routing information also connects and gives the detail of which layers are connected. Like somewhere the ports are in the first layer.
Routing, of course, will give you all the details of which layers you are connected. Yes, but typically when you are connecting modules at a high layer, you just try to keep most of the interconnections at the metal layers, but for some connections at shorter distances, you may use also other layers.
But how often do we do this post layout simulation in digital designs? We haven't.
Post layout simulation, see, you may not be doing it frequently, but it is a very good practice to it, because I am giving a very good example. You have done a design, you do a simulation at the high level without going through post layout, and you may see that your circuit is working at 1 GHz, you are very happy. But you get your chip fabricated, it comes back, you see that your circuit is working at 50 MHz only. That is the fact of life. You have ignored capacitances, inductances, the noise, crosstalk, everything you have ignored. But once you do a post layout simulation, you can find out the problem areas of the circuit where the delays are occurring. You can possibly redesign that part so that the bottlenecks are removed.
Sir, if in placement only we are deciding which interconnections to be done, then what is done in routing?
Placement, we are deciding the exact geometries of the blocks. The interconnections are done in the routing phase.